hunting down broken SSL in Android apps. To be honest, after 3 talks about broken SSL implementations, the cipher hell and all the other stuff, I'm not really surprised what other things can happen in with SSL. Okay, Matthew Smith from the Leibniz University in Hanover will tell us about SSL in Android apps. Thank you.
Thank you for the introduction. Hello? Okay, good. Okay, thank you for the introduction. My name is Matthew Smith. I'm from the University of Hanover, from the Usable Security and Privacy Lab. I will be presenting this work on behalf of my PhD student, Sascha Fahl, who unfortunately fell ill yesterday evening and can't attend. And the work's about hunting down broken SSL in Android. And yes, SSL is the poor kid on the floor who we're all kicking repeatedly in different and creative ways. So when we're talking about SSL on Android, we're moving away from the desktop system, and one of the really big paradigm changes mobile computing brought is that there is an app for everything. Unlike the general purpose browsers, we have lots of little apps which do things, and one of the things most have in common is that they share data over the internet. And some of them even attempt to secure this data transfer using SSL. And as probably everybody in this room will know, that SSL is a cryptographic protocol, and it is one of the mainstays of our internet security, and we use it for authenticity, integrity, and confidentiality, at least in theory. And we've heard a number of problems already, and Henning mentioned this slide in his talk, so I'll just very briefly recap this. Currently, we trust 100 to 200 different certificate authorities to sign any certificate anywhere on the internet. And SSL and HTTPS is only as strong as the weakest link in this big graph. And there have been real-world attacks against certificate authorities. So this is a very real threat, which Henning did talk about. And we're going to completely ignore now. So for a moment, we will pretend as if the CA system was up and running and working well. And we'll see that even if that is the case, we still have a lot of problems on Android. So using the current CA system, if you get a certificate, there are several steps you need to do to check that everything's okay. The first thing is you check, was the certificate signed by a trusted certificate authority? Then you have to check, is the certificate expired? And the wording here is actually quite important. I'll come back to that a little bit later. Then you should check if the certificate was revoked. And you should check if the host name verification succeeds. So that's where you actually check, I'm trying to reach domain X, and is the certificate actually made out for this domain X? And on Android, it does look fairly okay. So those 4 issues are all here, as you can see, added by, or they all have a little green tick, although there are 2 in brackets, and we'll look at those in a moment. But basically, they did think of everything, and they do try to do everything. Revocation in Android smaller 4.0 is a little tricky, so there's no straightforward way of doing that. In Android 4.0, they introduced certificate blacklisting. And I know there's a whole host of issues with certificate revocation, which we'll also ignore for the moment. But in theory, there is a system in place which you can use. And the next thing which we need to consider when looking at SSL on Android is host name verification by default is only done for the HTTPS connections. So if you, for instance, use the Java Net SSL Socket Factory, on Android, you will not necessarily get host name verification. We'll get into that a bit more later on. Angela mentioned that usability is a big issue, and usable security and privacy is very often approached from a very end-user-oriented perspective. So how can we create graphical interfaces which make things easier? How can we automate things? And I would like to make the argument that usable security and privacy is all the more important for developers and for administrators. And to make a point, we're going to have a look at the documentation we get if we use the SSL Socket Factory. So this is the Java doc. Where's my mouse? Here's my mouse. For the SSL socket factory, and the first thing you always get is a description, what does this class do? And in this case, it's very short and succinct. The SSL socket factories create SSL sockets. That's nice, it's to the point. And it sounds quite good. I mean, SSL sockets, SSL should be secure. Now we go a little bit further down, go into the nitty-gritty details. And the method createSocket says this returns a socket layer over an existing socket connected to the named host at a given port. Okay, we can see that kind of correlates with the stuff we're giving the method. And again, it sounds okay. I mean, there's nothing there to raise any red flags. And if we scroll further down, we see some more details. And here we have a look if we kind of use the default stuff, which sometimes happens. And this kind of stuff, which is kind of okay. And here's actually a bit of a warning. It says, if SSL has not been configured properly for this virtual machine, the factory will be inoperative, reporting instantiation exceptions. Now that sounds really good, doesn't it? I mean, it says if SSL wasn't configured correctly, it'll throw exceptions at you. So you'll find out what happens, which is good. Read all the rest, also all very boring. And here the create socket, again, a lot of blah blah, and just highlight a little bit, this constructor can be used when tunneling SSL through a proxy or when negotiating the use of SSL over an existing socket. Again, all this sounds good, secure, there are no big warnings. And this is a huge problem because nowhere in its entire document does it say that there is no host name verification when you use this SSL socket, which basically means this SSL socket does not protect you even one bit against an active man-in-the-middle attack. And that's something you would really expect the class not to do. I mean, you're creating an SSL socket specifically to protect yourself from man-in-the-middle attacks. It doesn't do it. And if there is a reason, and I can't really think of a good one, why this should be the case that you have to do that manually afterwards, it should be really explicitly stated in this document, which of course, as you can see, it isn't. There we go. So what you should use instead, Android created its own socket factory, which they call the SSL certificate socket factory. Again, naming-wise, maybe not the best idea because I'm not quite sure what the difference between the SSL socket factory and the SSL certificate socket factory is. But at least if you go into their documentation, they do have a big warning saying, don't use this one, they screw it up. But that, of course, only affects people who create their own sockets, and that is not something which is all that common. Most apps use HTTPS, we'll see that a bit later on as well. So the default way for Android to deal with HTTPS is okay, it's not broken. So the question is, why are we holding a talk here? What could possibly go wrong? And of course the answer is a lot. If you want to use SSL on Android, you have to go ahead and get your certificate signed by one of the roughly 130 pre-installed trusted certificate authorities, and some of them are fairly strange. Yeah. Oh, so the question was, is this something specific to Java on Android, or does this apply to all Java applications? This basically does apply to all Java applications to a certain extent. Android does make things a little bit worse in some ways because you have more little developers working on. So on the desktop side of things, you tend to have less apps, more consolidation, more use of big libraries, which sometimes make things better. But yes, this is a problem which you have on the desktop as well. So the SSL socket factory is broken on the desktop as well. Yes, exactly. So some of these authorities which we're trusting are fairly strange. So this certificate authority is issued to blank with the common name blank. The organization is the government root certificate authority. The serial number is there, and it's issued by blank with the common name of blank. doing some research, you find out this is, I think, from the Taiwanese government, and it is installed on a fair number of real Android devices. I'm not quite sure why I'm supposed to trust these guys, because, I mean, they are quite open about who they are. But again, I like bashing the CA system. I'll stop for a moment and go to the actual problems which are only there for Android. And that's the thing, if you don't have a certificate signed by a trusted authority for whatever reason, and there are some good ones as well, or if you want to customize your SSL handling in any way, you have to write code. And some of the reasons why you might want to do that, which are kind of good reasons, is you might want to do SSL pinning, so that would add security. You might want to add some error handling, or you would like to use a custom certificate authority like CA cert. So there are some reasons why people want to modify what's going on under the hood. And there are three ways you can do that. You can modify the trust manager, you can modify the host name verifier, and you can play around with a web view client for handling errors. And we kind of stumbled across these issues when we were building our own apps, and we were looking for ways of working with certificates. And we were doing what most developers do. We asked Google how to do something, and we found lots and lots of forums filled with stuff. And frighteningly, most of the questions asked in the context of Android and certificates was, does anybody know how to accept a self-signed certificate, or how do I get rid of these pesky errors? And almost all of the answers we found were basically answers which turned certificate checking off entirely, which of course does make the errors go away and does allow you to use self-signed certificates. It also completely defeats the point of using SSL. So we decided to have a look how widespread these problems were, and we downloaded 13,500 of the most popular and free Android apps from the Google Play Market, and we built a tool called MalloDroid, which helped us analyzing this code base, and this is a tool which is is now released, and you are all heartily invited to use it to play around with as well. It's based on the AndroGuard reverse engineering framework, and it identifies apps which contain code which is vulnerable to, or which makes SSL vulnerable to man-in-the-middle attacks. Some of the more simple patterns we detect automatically and actually flag as this is a definite problem. In many cases, we will just tell you there is code contained in this application which could potentially lead to a real-world problem. And in these cases, we also automatically decompile the app for further analysis and give pointers on where to go and look. And it's a fairly simple tool. Just have a couple of command line options. You can get some additional XML output, and you can decompile the files. But basically, it's just a single command line. You call our script, give it the app you want to check, and optionally tell it where to decompile the files to. And you can try that out yourself. The GitHub URL is here. And what you will get is an XML blob with all sorts of information which will help you find out if the app you're looking at is actually broken or not. So here's a sample output of an antivirus app I will show you a little later on. And as you can see, there are lots of little tags here, broken equals true, which is not a good sign. It'll go through all the code places we identified where we can modify SSL, and it'll check all those against patterns we know and flag any places where users have created their own code. And it'll give you the method which has the dangerous code in question. And as I said, it'll go through all those things and give it to you. However, it only finds the definite proof in some cases, but it does flag all the suspicious code, which you then have to go and look at yourself a little later. So before we go into that, just some brief statistics of what we found in our sample. As is to be expected, most apps use internet permission, and most of the networking API calls are HTTP and HTTPS. Very, very few apps use exclusively HTTP, most are mixed mode. And in 17.28% of the apps which use HTTPS, we found code which was in principle vulnerable to a man-in-the-middle attack. And most of that was based on custom trust managers, and I've selected 22 of the ones we found. I've selected several of those 22 we found. And if you have a look at the names, you have some which stand out. So you have the non-validating trust manager, or the fake trust manager, dummy trust manager, and accept all trust manager. These are all names where you pretty much know what you're getting into if you add that to your code. But again, there are some which are fairly dangerous. So the easy X509 trust manager does sound like something quite pleasant. I mean, X509 is complicated, it's annoying, and this one makes it easy. So that's something you might want to use, and if you don't check, you will not see that, in effect, this turns off validation. Also, the simple trust manager, the open trust manager, these are names which don't necessarily raise any flags if you're using them. And we conducted lots of interviews with developers of effective apps, and they are quite often said, well, we used this library, and we thought that was a good thing to do, because you shouldn't write your own code, you should use libraries. And yes, that's right, you should. But of course, you do have to check these libraries are doing a good job, and unfortunately, in this case, most of them don't. So just to give you an idea what these things look like, so we have the check server is trusted, and in 90% of the cases we found it just says return true, or it just returns without doing anything. So a man-in-the-middle attacker can inject an arbitrary certificate because there are no checks whatsoever, the method just returns. And all in all, we must say, if you're analyzing an app for a customer and you find a custom trust manager, odds are it's breaking SSL. So that's one very simple thing to track, even if you don't use our tool. If you see one of those, it's probably not a good thing. But there are also other cases where people are trying to do things which actually make sense. So we have almost 10% of the custom implementations which customize the check server trusted, and they then get the certificate and then they check the validity. And I mean, that's a good thing, because that doesn't necessarily always happen by default, they think. This is now something I'd ask the audience. How many of you think that this checks the validity of the certificate? No hands. We have a very cagey audience. Wait, actually, it does check the validity. I mean, that's its name. The question is, can someone tell me what the certificate's validity is? Yes? Exactly. So, in this case, validity is defined as from when to when, time-wise, is the certificate valid. It has nothing to do with is there a valid signature or is it the right name. But of course, if you are a programmer and just say, oh, I have to check something, I'll press the dot and see what Eclipse offers me, and you find this wonderful method which says check validity, that does kind of suggest that you are checking if the certificate is valid. Just plain English suggests that. And there's another instance where usable security for developers is really important that we start thinking about it, because these are mistakes we force people to make. I mean, we are the guys who make these kind of libraries, who make the APIs, and it's the normal developers who then get fooled by us and make mistakes, which then get papers by us published on good conferences. So, slightly perverse incentive here that if we continue doing this, we can publish papers about it. But all in all, what MalloDroid will give you is a static code analysis. So it doesn't tell you necessarily that something is definitely broken, because it just says there is code which is broken. That doesn't mean that the code has to be executed. It might be in a dead part of the execution tree, or it might not necessarily mean that code is actually dangerous for users. So for instance, there could be some code saying accept all certificates if debug equals true and developer equals true. In which case there would obviously be kind of some flags which the developer can set to disable certificate checking in certain cases. And that might be completely fine. So these 17% of apps we found might not all really be broken. So what we did is we picked 100 apps from the big sample and did some manual checking. And in 41 of those, we actually could execute a man-in-the-middle attack in real life, and we captured credentials for a whole host of services, and including credit card numbers, PayPal, bank accounts, Facebook, all kind of the big services. And one of the critical things here, very often we capture credentials of big name companies because of third-party apps. And that's something which is very annoying for the big name companies, because now it kind of looks like that American Express had a security problem. It was a third-party app which leaked information. The same with PayPal. The PayPal app itself is fine, but other apps messed it up. And these are, even though they're third-party apps, they have a large install base. So just these 41 apps had an install base of somewhere between 40 and 185 million installs. And that, of course, is a massive user base you want to attack. And just to give you some ideas of what kind of things happen there, I'll highlight one of my favorite applications. I do apologize to the people who were on the DFN workshop who have already seen this. But this is an antivirus app, one of the few which is actually not scareware, but actually does do something good on Android, and it was also awarded the best free antivirus app by a test. And when it gets its signature updates, it does it correctly. It does use SSL. Unfortunately, it doesn't verify the host name. So we went into the code and found the do not this variable do not verify, and it just returns true on verification. So this was fairly obvious that it wasn't doing what it was supposed to in the global sense, but it was still built in. And just a little demonstration of what it looks like if you then get an app like that. And there's also tools you can get from us. We have a little rogue DNS server which allows us to mount an active man-in-the-middle attack. And we then created for this virus app a little program which would create a new virus database. We give it the checksum of an app which we would like to blacklist as a virus. And then we start the phone and the antivirus app, and we activate the update mechanism. Now our rogue DNS server redirects it from the update server to our malicious database. It then updates it, and as you saw, that all went fine. So we start the scan. It'll now scan the entire Android system. I think we abbreviated it slightly, and it found the threat, and it found itself as a threat. So we gave it its own signature. And that was kind of already the success we were hoping for, and just for fun, we clicked on remove, and it said this application will be uninstalled. And then it does. So this antivirus program obligingly shot itself for us based on its own algorithms. This is presented with kind authorization of Zone Antivirus, who were one of the very quickest to fix the bug, and said we were allowed to use this as educational material. So very nice developers, but also very skilled developers. I mean, they were developing antivirus software. They knew what they were doing, and even they did make a mistake, which was pretty bad. And there are lots of examples. So MalloDroid, an app which does online banking for over 60 banks, and PayPal, Steam Wallet, Eurocard, all sorts of stuff, has plugins for different banks and different accounts. And 26 of the 41 accounts you could access were broken, and there was no user warning. So they hid all errors which came, and we found apps which would allow us to remote control the apps, remote code injection, we could unlock rental cars. There's a whole host of stuff. So we then kind of sat down and said, this is such a widespread problem. When we're kind of trying to hunt down the causes of this, just finding apps which are broken is fun in a way and does help, but it will not eliminate the root causes of why things are going wrong. So we contacted the 80 developers which were responsible for the cherry-picked apps we had, informed them of the problems they had, and offered assistance in fixing the apps. And after that, we asked them if they would be kind enough to participate in a survey and would allow us to interview them about this. We, of course, offered them anonymity, so we wouldn't mention specific answers. And surprisingly, 15 developers agreed to these interviews. Most didn't answer at all. Some answered and said, for legal reasons, I'm not allowed to talk to you. But we still got 15 people to talk to us, and that was really insightful. We'll just share a couple of the highlights, which seem to be indicative of the larger scale problem. So we have people who say this was one of the first mobile apps we wrote, and when we noticed there was a problem with SSL, we just implemented the first working solution we found on the internet. And this does seem like a very, very common approach. And they said we usually do build Java backend software for large-scale web services. So here we have developers who are experienced in another area coming into this booming mobile market, and they then just have to, under time pressure, start building something. And they go to the first solution they find, not always checking things. And again, we are bashing developers quite a bit in this talk. And I would like to state again, this is not necessarily their fault. I think this is a fundamental problem we have in developing security software, and it's not the developers who are the dumb ones here. We are making things too hard for them, because these are people who are experienced software developers, but they mess up something so critical to their software. And this is another example going in the same direction. Here we had someone who said, okay, after you told me what had happened, I opened up Wireshark and checked, and I checked if there was SSL on, and I saw all this encrypted stuff. I don't see the problem. So here we have someone who has enough tech expertise to operate Wireshark and to set up things that he can use it and can analyze his protocols, but he didn't understand what a man-in-the-middle attack does. So that was the component which was missing. So he just mounted things and checked the traffic without attacking it. And of course, if you check that, you see the encryption and you believe you are safe. We also have some interesting cases where people said, yeah, we know, and we're not going to change it. We have one really big app which said we have customers who say they want to connect to their servers which have self-signed certificates. And the only way we could make that usable was to always accept all certificates, which is a very strange choice, and also one which the users never saw. And finally, also something which seems to be very common, people who use self-signed certificates for development purposes. So they said, oh yeah, we built that in so we test in our lab, and we just forgot to take it out again. Again, easy to happen, because I mean, we all know when we're developing stuff, things get tight and we have to work very quickly. And something like that just, it doesn't bite us because there's no error unless there's an attacker. So to summarize kind of our search for the root causes of these things, we kind of got these guiding points which we think are important to think about when we're trying to fix these things. So developers have a need to use self-signed certificates during development. This is completely legitimate, because you don't necessarily want to spend the time and money setting up correct certificates when you're just kind of playing around and getting things starting. There are also some cases where we would say there is an argument to be made to use self-signed certificates even in production environments. Not that many, but there are, and unless we can re-educate all developers worldwide that they are never allowed to do that, we should be thinking about ways that we can enable that kind of use case without endangering all the rest of the ecosystem. But one of the things which we found again and again and again was that the code complexity on top of the underlying complexity of SSL in general was just too much for the developers. They said, we aren't security experts, we want things to work, our main goal is to make the app functional, and we try our best with security, but it is a limited resource and things are too complicated. So those are the kind of the problem cases. We also kind of heard two other points I'd like to raise, and that is one, when talking to them, we kind of try to find out if they knew about the kind of the more advanced methods of securing things, and once we told them about certificate pinning or creating their own trusted roots, there was a lot of enthusiasm. They said, that's a great thing. I really like the idea that the governments of the world can't decide who I trust. I can decide for myself, I can pin that to my app, but I have no idea how to do it. Giving them code snippets to do it helped in some cases, so some actually implemented it on their own, but again, the code complexity is difficult and you have to start customizing SSL to do it. Another thing they kind of said, especially those who kind of accepted things without showing any warnings, they said, well, I would have to invest a lot of effort to create a warning system, and that's something which is, again, very surprising. There is no way for a default warning to be shown. It is all down to the developer. He has to decide what to show, when to show it, and how to react to that. And anybody who's familiar with the usable security and privacy research domain knows that creating good SSL warnings has been a hot topic in research for many, many years, and there are many studies showing why the current warnings are terrible. And there are big teams working on that to kind of create the perfect warning. And here we are saying every single app developer should do it themselves. And that just is a recipe for disaster, and we'll see one or two examples a little bit later on. So any kind of solution we're going to propose will always be multi-level and multi-step. So kind of a stopgap takeaway we should kind of take on board right away is that broken SSL certificate validation is a serious problem right now, and there are many apps which have this problem. And if you are a penetration tester, if you are a security tester, just know that, look for it. You're welcome to use our tool. Again, you can download it, and it's very easy to use, and you can then just find these apps and kind of start educating people on how to do things better. But even if we get all that fixed and people start developing secure code, we still have the problem that even the good apps aren't really good yet. So while they technically don't endanger the user, they do suffer from serious usability problems. So many apps just kind of crash or hang indefinitely. So if you attack them, they just freeze up. And others give you very interesting warning messages. So my favorite one is Flickr. It says, sign-in error, oops, a little hiccup here. Please adjust the time on your device to the current time. Now that has nothing to do with what actually went wrong. It'll confuse the heck out of the user, because they'll look and say, well, this is the time, what's going on? And then they might start messing around with some settings, and definitely not a good thing. And this one is debatable. And I'll just give you a minute to read that. So which of you think that's a good warning message? Well, who thinks it's not a good warning message? Okay, most of you. And that was something I was arguing many times. In one talk I held showing this warning message, someone actually put their hand up and said, I think that's a good warning message. And they actually made a sensible. So what I always say, what's bad is only if you go into this cryptic stuff do you see that there's some kind of certificate issue. Because this above here says, the login failed, please check your network connection and try again later. And I said, that's not good because it doesn't tell the people what's going on. And one argument was, well, maybe it's not a good idea to tell them all that, because basically it stopped the connection, so it doesn't give them the option to continue on. It just says, try again later. And if the attack's still there, it'll again pop up and stop them from going on. And at some point, they will then go to someone who knows what they're doing and say, listen, I can't get on. And then the technical person will be able to react and say, yeah, I know what's going on, and we need to check this. Or if they were just in an internet cafe and the attacker was in that network, they'll go home and they will use their system, and they will have not lost their credentials. They will not be able to click continue anyway because I want to check my Facebook messages. So maybe this warning isn't quite as bad as we think. But this is something which is open to debate, and we certainly don't have all the answers yet. So let's say we got all that fixed. So the code is okay, the warnings are okay, and we're still not safe. Now we're coming back to this CA problem I mentioned in the beginning. So if you don't have a root certificate authority you can just use to attack people, Android has another very nifty little problem where it comes to certificate validation. It's very easy to create your own certificate authority for Android. And we decided to conduct a little study to see how easy it actually is. So we did an Amazon MTurk study, which we dubbed the usability of Starbucks free Wi-Fi. And we showed them they could only do it via their Android mobile device. And they showed them this, and they said, if you want to connect to the internet, we're giving you a new secure Wi-Fi. You get a certificate, and that'll make you really safe. And you click the connect and add certificate, and then you're good to go. And we then showed them the certificate dialog. They would have to name that, and then what they would then in actual fact do, if this was a real attack, they would have installed a new trusted root authority. of the 143 participants, we had to throw out a couple who just clicked through. We had 128 participants who conducted the test faithfully, and 73% accepted our login method, installing our root certificate in this simulation. And to make matters worse, 77% believed that they actually made their own system safer by doing that. Of those who clicked cancel, most strangely believed if they had installed it, it would have made it safer. So they decided to cancel for other reasons than safety. 30% believed it wouldn't have changed anything. Only 6% thought it would have had a negative effect. So we see this kind of just saying install something which will make you safer is a very good approach to getting people to install root certificate authorities. And as we saw in the beginning, once you have that, everything is open to you. We did some standard questions on how they thought the usability of our new improved Wi-Fi login method was, and we got very good scores, so the usability was fantastic. And it just means that the complexity of the CA system and everything surrounding certificates and SSL is so bad that it is an invitation to attackers to mount human human-targeted social engineering attacks against this, because we are so used to things being difficult and clicking away warnings, or having our institutions say, well, you have to install our company's CA. So we are used to doing this stuff. And Android has this fairly bad security feature, good usability feature in some ways, that this dialogue with which they install the certificate is very easy to use. It's something normal users shouldn't really be doing, and it adds, without any warning, a certificate which is then trusted globally throughout Android. So this is kind of what we discovered while we were hunting down all the SSL bugs on Android, and we of course have been working on some countermeasures, and we think one of the big takeaways, the final takeaways, is SSL code should not be in the hands of developers. This is just something which is a recipe for disaster. We should find ways of enabling the same security for the average developer without having to make them write code. And we designed a system which would allow them to do exactly that. So we created a custom Android which allows people to configure SSL for their apps using the manifest file, and they can add pinning without any problems. They just add the fingerprint in XML, and we tested that with a number of developers who had broken apps, and they loved it. So they really liked the idea of not having to code to get their apps safe, because they do want it to be safe. And as a side note, one of the nice things of taking the SSL code out of the apps and into the operating system, into the security experts domain, is we have a single point where we can modify the system. So Henning was talking about all these different options of improving the CA validation. Unfortunately, in the Android domain, if there's custom code around, every single app might have to be changed before we can run a new change. If we take the system down a bit, like we're suggesting here, we have a pluggable framework. We can say we're now going to roll out certificate transparency for all Android apps, and we can switch it on like that. And we think this agility is something also which is really important. And if you're interested in hearing more about the countermeasures, we will be presenting that in Berlin on the CCS, and I do hope that many of you will come there. It's really important that we get this conference really successful. It's the first time in a long while that it's left America. It's the first time in Europe, so we should have a strong European presence on this conference to show that we are doing good and plentiful security research here. Okay, so thank you for your attention, and I'm happy to take any questions. Yes, Dirk.
Thank you.
The Python script, does it include a complete decompiler of Java, or what would you...
No, so
Can you repeat it?
Oh yeah, so the question was, does the Python script contain a complete decompiler? No, the script depends on AndroGuard, which is a decompiler. So you have AndroGuard, and our script then calls AndroGuard and adds all the magic we showed here.
Next question.
Yeah. So the question was that I said that most of the big leaks came from third-party apps, not from the apps themselves. If I could elaborate on that a bit. So the PayPal credentials and the American Express credentials were leaked by third-party apps which had payment options included. The banking credentials were leaked so one was this big open source app which had lots of banks as plugins. But we also had, I think, 2 official apps from banks which had broken SSL, so they were the real deal which had broken SSL. It turned out they had outsourced their development to another company, so they had a branded app created by someone else. We then did some research on that company and found that company specialized in creating customized online banking apps for little banks and had rolled out broken SSL for all of their customers. So we found a whole range of further issues there. And they were not very happy with us, which I think is a little bit surprising because, I mean, we didn't name them. We called them and said, this is the problem. And we actually had one call from a bank who was really shocked, and they said, so we said, you have this and that problem. They said, no, we don't. Our app is secure. We know that. And we said, no, listen, this is how we set it up. This is what we attacked. This is what we saw. And he said, you attacked our app? Yeah, in our lab. He said, well, no, we still don't believe it's broken. And he said, well, listen, if you go to your source code, line 80-something, and then there was a bit of silence, and he said, how do you get our source code? Yeah, we decompiled it, and he said, what? So even the guys in-house, so the main party apps do have issues. But many sites, I mean PayPal, Facebook, they all have these apps which log in via Facebook, pay via PayPal. And if any of them screws it up, they lose because, and that's maybe the fault of PayPal and co, they still have the HTTP version or the unsafe version. They should pin, oh no, actually they can't, sorry, no, I take that back. They can't fix that. Yeah, they're screwed.
Yeah. Dave?
No, actually we didn't. No, we didn't do that. So we contacted all the app developers and we contacted Google. We didn't. Okay. Yes, please do.
Right.
Yeah. Yeah, could check that.
OWASP brings the right people together, I see. Okay, thank you, Matthew. It's a wonderful or maybe an ugly example for the well-known lesson, complexity kills. Let us imagine that every developer has to write its own IP version 6 code, yeah?
Yeah.
Everybody will say, no, this must never happen. No? But why about SSL?
Absolutely.
Okay. Thank you, Matthew.
Okay, thank you.
It was